Hi, and welcome to 10.6 Potential Difference, also known as voltage. In this lesson, students will be able to describe potential difference and calculate the voltage of a charge in an electric field. So, in describing what potential difference is, it's useful to draw a parallel to something we're more familiar with, which is gravity. So we're going to compare the non-contact field forces, which, by the way, saying that a field force is non-contact is a little redundant, but we're going to compare gravitational force and electric force in order to define potential difference, which is measured in volts and also known as voltage. The equation that we're going to get to is V is equal to W over Q. The voltage is equal to the electrical energy or the work divided by the charge, the work per unit charge. So, this equation doesn't look too scary to deal with. You're plugging in numbers just like usual, but what the heck does it mean? So I'm going to attempt to describe what the work per unit charge means. It seems like it gets a little bit complicated in my description as we compare the gravity and the electrostatic force. But just keep in the back of your mind that it might get a little scary over the next minute or so, but we're really just coming to V equals W over Q. So that's going to be the main idea for the lesson. I want to give you a little bit of a derivation, or at least like an understanding of what potential difference is, instead of just calling it, okay, it's the voltage, it's measured in volts. Potential difference. Difference between what? So let's compare gravity and electrostatics by just starting with gravity. Let's say we have the Earth right here. All right, that's the surface of Earth. We know that Earth has a gravitational field around it that is attractive, right? Things fall down towards Earth. And we can measure the strength of that field as Fg over m. This is like Newton's second law, A equals the net force divided by the mass, but we're using it for the gravitational field strength. Let's say you put a mass in that field. What's going to happen to the mass? It's going to feel a force. So that force that's felt is equal to gm, the mass of the Earth, times the mass of whatever object you place here, divided by the radius squared, the distance squared, okay? So this is saying the gravitational field strength measures the field itself, and it's not dependent on the mass. The field was there before the mass was there. The field was just fine, and we could measure the strength of the field. The force due to gravity measures the force felt by that mass. So this is dependent on the mass. You need to have a mass here in order to feel a force, but you don't need to have a mass here in order to measure the field strength. So that's like one relationship there, and we're going to use that relationship again, okay, where you have a quantity that's dependent on the mass and a quantity that is independent of the mass. See where we're going with this? How the mass is on the bottom there? It's independent of the mass. We're just describing the field. Okay, so that's cool for force, but what about like energy? Let's say we exert a force on that mass. Work is required to move the mass against the gravitational field. The mass gained gravitational potential energy, and the work that you do is equal to the change in the potential energy. It had some potential energy here. Now it has more potential energy. Where did it get that additional potential energy from? The work that you did in moving the mass. Cool. So the gravitational potential energy is equal to mgh. Now we're going to introduce something new. We saw all three of those things before. We don't really talk about what's called gravitational potential. We talk about gravitational potential energy. This is what gravitational potential is. So we know the work you do is equal to the gravitational potential energy. That's equal to mgh. Let's find a physical quantity like g, the gravitational field strength, where we're measuring the potential energy on the field independent of the mass. So it's not actually the potential energy, it's just the potential of the field at that point. So the way we get it independent of the mass is we divide all of these quantities by the mass. This cancels out, and the gravitational potential energy divided by the mass is known as just the gravitational potential difference between those 2 points that we showed before. So this is like a new concept. The gravitational potential difference is the work per mass of the field. So the gravitational potential measures the field itself, and it's not dependent on the mass. It's a way to measure the difference in the potential between those 2 points. Whereas the gravitational potential energy measures the energy of this particular mass. So it is dependent on the mass. If you increase the mass, your gravitational potential energy will increase. But just by placing more mass here, it's not going to change the gravitational potential difference of the field itself. You can put as much mass as you want there. It's not going to change the potential difference of the field itself. So now we have kind of an idea of gravitational potential, and that's going to be analogous to the electric potential difference or voltage. So let's do the same thing and build up to that like we did before. Now we have a metal sphere with charge Q, and we have an electric field around that charge. We can measure the electric field strength by doing the force felt divided by the charge. Okay, so now we have a measurement of the field independent of the charge that you place there. Let's say you do place a charge there, and let's say it's attracted. By the way, in this little thing, this would be a positive test charge, and if it's attracted, that means this would be negative. And you could have the same thing if this is negative, but you put a negative thing here, you're going to feel a different force this way instead of that way. So that's where it's another little step with electrostatics, makes it more interesting, whereas for gravitation, it's always attractive. So just something to keep in the back of your mind, but let's continue with this. So let's say you do put a charge there, it's going to feel a force, and that force is equal to K, the source charge, times the amount of charge that you place there, divided by R squared. That's how you determine the force. And that is dependent on the charge. So this says the electric field measures the field itself. It's not dependent on the charge. You're dividing out this charge. You're just measuring the strength of the field. The electrostatic force measures the force felt by this particular charge. So it is dependent on the charge. And remember, we're going to do the same thing we did before. We'll talk about a new concept that we didn't talk about, the electric potential energy. So now, this is attracted to the source charge. You could do work and push this charge upward. You could move it in that electric field, but you need to do work in order to do so. Work is required to move the charge against the electric field. The charge gained electric potential energy. That change in electric potential energy is equal to the work that you do on this particular charge. Can you think, what would this formula look like? I'm going to have the next thing is delta EPE, the electric potential energy, is equal to what? What are the analogous physical quantities that we're going to talk about? If you want, you can pause the video here. What is the mass? What is G? What is delta H here? So this is what it looks like. You have the charge instead of the mass. You have the electric field strength instead of the gravitational field strength. And typically we'll use distance instead of height. We use height for gravitation because we live on a planet. So to us, it's like, oh, that's a height difference. But if you're in the classroom and you have a metal sphere and a different metal sphere, you're just measuring the distance between these two. All right, or the distance here. So this would be the distance here, the change in your distance is that. So QED, that's the electric potential energy. That's the energy of this particular charge. All right, it had electric potential energy here. It gained electric potential energy for that particular charge, but let's describe the field itself. It's more useful to be able to describe the difference in the electric potential between these 2 points, or the potential difference, or the voltage. So now we're going to derive that equation. This is what we have, QED. Let's make this independent of the charge. Let's find a physical quantity like E where we're measuring the potential of the field instead of measuring something that is dependent on the charge. So let's divide out the charge. Okay. So this is not the electric potential energy. It's the electric potential energy divided by the charge, otherwise known as the electric potential difference between 2 points. And that's going to be equal to the work per unit charge. So the electric potential difference between these 2 points is equal to W over Q. The electric potential difference measures the field itself. It's not dependent on how much charge you place here because we're dividing it out. We're just describing the field. The electric potential energy measures the energy of the charge, so it is dependent on the charge. Potential difference is also known as voltage, and this equation, work per charge, that's the equation for voltage. Beautiful. So now we're ready for our traditional note slide. Hopefully you have a better understanding of what this potential difference is, which is also known as voltage, and we use a capital V to represent it before I go over the definition. So hold in your mind what we just talked about as I read this. It says the work, potential difference is the work that must be performed against electric forces to move a charge between the 2 points in question divided by the charge. So it's the work that must be done. Oh, is it the energy? Is it the electric energy? No, because you're dividing it by the charge. It's independent of the charge. The units for voltage, confusingly enough, are volts. You could also write joules per coulomb, J/C. The reason they're called volts, they're named after Alessandro Volta, who invented the voltaic pile, which was the forerunner of the battery. So they could ask, what is the potential difference? Or they could ask, what is the voltage? And for either one of those, you give your answer in terms of volts. And as we said, the equation is the voltage is equal to the work divided by the charge. So where is the formula for potential difference or voltage? It is located on page 4 in the electricity section. It's right here. The voltage is equal to the work divided by the charge. Now, in the word problems, they might say, what is the potential difference? They might not say what is the voltage. So don't just be hyper-focused on the V. Remember that the V is equal to potential difference. So if you forget, just look over here for the words potential difference, and then it'll remind you, oh yeah, potential difference is equal to the voltage. The other thing I want to point out is that the W is equal to the work, or they also call it the electrical energy in this section. So just so you know, if they ask for the electrical energy, you're looking for W, the work. Let's talk about what a volt is a little bit more in depth. It says there is 1 volt of potential difference between 2 points when it takes 1 joule of energy to transfer 1 coulomb of charge between those 2 points. So let's say you have 1 coulomb of charge here, and it takes 1 joule of energy to move it here. Then the potential difference between these 2 points is 1 volt. Okay, it's 1 joule per 1 coulomb. Now, let's say it does take energy to move it here. What is the charge of this metal sphere? Is the charge positive or negative? Pause the video and think about it. Well, if we need to do work to move it this way, that must mean it's repelled by this. So that must mean if this is a positive charge, as shown, this metal sphere is positive. But what if it was negative? Let's see. If it was negative, it takes work to move the charge from this position to that position. Now it flipped the A and the B. So it takes work to push it away. This is kind of more similar to like if this was planet Earth and you're lifting it up in the gravitational field. This work equals the change in the electric potential energy of the charge. The electric potential is higher at point B than at point A. The interesting thing about electrostatics is you could have attractive forces, but you could also have repulsive forces. So now these two are repelling each other, and you're gonna need to do work to move it to point B. It says it takes work to move the charge from A to B. This work equals the change in electric potential energy of the charge. The electric potential is higher at point B than at point A. So you have to think of how they're repelling. Let's do a quick example here. It says it takes 6 joules of energy to move 3 coulombs of charge from position A to position B, right? Because again, this is an example where it's attractive, almost like Earth, and you need to do work to lift it up away from here because they're attracting. So what is the potential difference between these 2 points? Well, we could do the guess method still. 6 joules of energy, we're going to call that W. And if you look in your reference table, it actually has W as electric energy. So the work or the electric energy is equal to 6 joules, and the charge is equal to 3 coulombs, and the voltage or the potential difference is what we're looking for. So don't get confused. If it says what is the potential difference, or if it tells you the potential difference, that's your capital V, okay? And then you could use the equation V is equal to the work per unit charge. So this is equal to 6 joules divided by 3 coulombs, and you get 2 joules per coulomb or 2 volts, okay? Now, erase everything else here. Let's say you stop thinking about physics for a while, and then you come back to this, and then you see, oh, V is equal to 2V. How the heck is that? How does that make sense? So then if it's like an algebra thing, don't get confused, because now this is the letter that we use to represent voltage, and this is the unit. So it would be like saying the mass is 2 kilograms, but instead of kilograms, we're going to just use M to represent, like, see how sometimes people get confused by that. The fact that the unit is the same thing as the letter we use to represent the physical quantity. So hopefully that's not too confusing. So here it says it takes 3.2 times 10 to the negative 18 joules of energy to move a proton from position A to position B. Again, now we flipped this and it is repelling, so it's going to take work to move it like down, quote unquote down, or closer to the object, which is the opposite of what gravity is all about. So yeah, it says what is the potential difference between these 2 points? So this is the work or the electrical energy. And that's the only number I see in the problem. There must be some hidden information. Yes, it's a proton. So the charge of this object is 1.6 times 10 to the negative 19 coulombs. And they're saying, what is the potential difference between these 2 points? Again, the voltage is equal to the potential difference, and that's what we're looking for. So the voltage is equal to the work per unit charge, and the potential difference is equal to 20 volts. Nice. Okay, so this is more of like a critical thinking question. It says, what direction should the positive test charge move in order to gain electric potential energy, lose electric potential energy, or keep the same potential energy? So, and it's important to note, now we're talking about energy because we're talking about a specific charge. So the terminology, remember, but pause the video and think about it a little bit. Okay, so this is being repelled by this. This charge is also being attracted to this negative plate. So in order to gain potential energy, you have to move it against what it wants to do. It wants to go this way. It not only is it attracted to this plate, it's being repelled by this way. If it had its way, it would just go straight down. In order to gain potential energy, you need to do work on it. So you need to move it upward, just like that. So that is gaining potential energy. We're moving it against what it wants to do. For it to lose potential energy, it just moves straight down doing what it wants to do. Now it lost its potential to do anything, right? It had potential here. That potential got transferred into kinetic as it moved downward. It lost the potential energy. To keep the same potential energy, if you didn't pause it before, pause it now. What would you do? You have to move it somewhere, but where would you move it in order to have the same amount of potential energy? You could either move it left or right. Anywhere on that line, you're still the same distance away from these charged plates, so you would have the same amount of potential energy. Anyway, that's about it. Thanks for watching and have a great day.